Okay, so we do have some problems, guys, but really quick, I'm just gonna share my screen on my, oh, can you make me co-host, Amelia? Really quick, I'm gonna share my screen on my laptop, and I just want to show you guys two quick things.
Try sharing.
Yeah, sweet. So the first thing I'm gonna share is this YouTube video. I know we already mentioned it. Let me know if you guys can see my screen. I'm not gonna play it, but we already sent you guys this YouTube video. And we did convolution. Let me drop it in the chat again. Now that you guys have had gone through signals a little bit more, I think you'll get a lot more out of this video. And I think he has some really cool examples. So just super briefly, he has like this one example where he has this Mario and he does some image convolution and he's able to show like, I don't want to play any volume here, but he's able to show like it blurs the image basically. So he goes a little bit into that. He shows like changing the color of some images. So it's pretty cool. If you're into this stuff, he shows some images of like turning black and white images into color based on like their traces and stuff. So it's pretty cool stuff. Would highly recommend. And time speed, it's like 11 minutes. The second thing is that before, when we were doing time series stuff, we were using just conv in MATLAB, but now the function you might want to look at is conv2, which is just 2D convolution. So now that we're dealing with images, this function might be a little bit more relevant. So just two things to point your way. Now let me share my screen and we'll get started into the actual recitation. Okay, can you guys see my screen? Yeah, okay, sweet. So basically just gonna do a quick recap for how convolution in the image space works. So basically we have two things here on this slide. We have our signal or whatever, we're interested in. And then we have our kernel. And I believe this is also called a mask, but don't quote me on that. That's like a Ryan question. So if I'm wrong, please interrupt. But I believe this is also called a mask. I'm not sure about that, but definitely called a kernel. And basically how we can take the convolution is we look at our kernel here and we take its center and we run the center over each point, and then we do kind of like a moving average. So we'll align the center here over each point and we'll slide it across. And each time we slide, so each instance here, we multiply the surrounding points of the signal by the surrounding points of the kernel. So for example, if I was going to choose to do this example here by taking this 0 and aligning it at this 50, basically you'll see here that we'll get 0 times 40, 0 times 46, and 0 times all of these. And then the only thing that will happen is we'll get this 1 times 42, and we'll basically add everything. So down here it shows the math, but you basically get 0 plus 0 plus 0 and a bunch of zeros plus 1 times 42. So if these were actual numbers, for example, maybe this is like a 2 and this is a 3. So what we would do is take this 1, get a different color here, this 1 times 42. So we'd have 42 plus this 2 over here times 46 because we're aligning it at the center. So plus 2 times 46 plus 3 times 55. So this times this. And we'd have to, there'd still be plus 0 because we also multiply all these things by 0. So plus 0 and a bunch of other zeros. But that's only doing it at one point. So now whatever this sum is, let's call this sum y or any variable, this y just goes here. So then you have to do that for each square, each part of the matrix, right? Each point. So that's point 1. And point 2 is that if you guys remember in the initial formula for convolution in just the time series, right? We have to flip our signal or flip our kernel around the y-axis, right? So now that was 1D convolution, but now we're dealing with 2D convolution. So if they give you some H before it's already been like quote unquote flipped, you'll have to flip it yourself. So that's probably, you most likely will have to flip it yourself. So how that works is now that it's 2D convolution, you'll have to flip it both horizontally and vertically. So just really quickly, I'll give you an example, horizontally and vertically. So let's say you have this signal or this kernel H, right? Let's call it H. And let's just say it's, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's a 3 by 3 matrix, 3 by 3. So it doesn't matter the order you do these, they're interchangeable. But for this step one, let's just start, for example, flipping it horizontally. Let's flip it horizontally. We would get something like this. So 3, 2, 1, 6, 5, 4, and 9, 8, 7. I would recommend doing these steps separately because you're much less likely to make a mistake. You can do it all in your head if you want to, but you're just more likely to make a mistake. And once again, these steps are interchangeable. So if you want to flip vertically first, that's cool too. So then after flipping it this vertically, we'd get something like 9, 8, 7, 6, 5, 4, 3, 2, 1. So the reason we didn't have to do that for the time series convolution is that's just 1D. So now that it's 2D convolution, we have to flip both ways. So if, for example, you were given a problem, you have this X signal, you have this H. Before you can actually do this process of running this kernel over each time point and performing the dot product, you have to do this flipping first. So you flip it, and then we could do that sliding process. So now let's hop into an actual problem where you're going to see that in action. So here's this problem. We're given this 4 by 4 matrix. Oh, and one other minor point is that this kernel, like 99% of the time, you're going to want it to be odd, and odd in terms of its dimensionality. So like 3 by 3, 1 by 1, 5 by 5. Like this is, I'm talking like in practice. If you, for example, have like an even, maybe it's like 4 by 4, I'm not 100% sure of how you're going to go about, finding the center. That's maybe also more of a Ryan question. It's a little bit out of the scope of the class maybe, but I just wanted to bring it up. You're definitely going to be given odd stuff for all your questions, so don't worry about that for your homework and tests. I'm very confident that they'll be odd, but just so if you ever, in the real world, you come across this, you might have to do some future research on like how to find the center of this. Maybe you just find the average. I'm not 100% sure. So just keep that in mind. And if it's non-square, like you're given something like this, non-square meaning that its dimensionality is not equal. So maybe in MATLAB, something like this, 11, 12. So it's not square because there's nothing here, right? You can just add a 0 here to make it square. And you can also add some zeros here. So that's called zero padding, just adding zeros to make it square. But if you're going to do that, you'd probably want to just add enough zeros. This is also probably a Ryan question, but add enough zeros to make it odd as well. I'm not quite sure what happens when, here it'd be 5 by 5. I'm not quite sure what happens when it's even, but just thought it'd be worth to bring up. Okay, so now let's do an actual problem that will be relevant for your homework and your tests and stuff. So here's the problem. We're given this X, so this is going to be our signal. And we're given an H here. So this is kind of showing the process of flipping it. So this H prime is flipped. And here's our kernel. And now the question is asking to find the output image Y that results from the convolution of filter H. So let's do that. And I'm actually not going to use this flip version. I'm going to walk you through the flipping just one more time so that way you feel good about it, because that's a pretty important step. Okay. Okay, so we have our X. Let's just rewrite that here. So your X does not have to be, odd. That's just for your kernel, because you're going to align the center of the kernel with each one of these time points, or each one of these samples or points. So this does not have to be odd. And once again, just take what I'm saying about the even and odd with a grain of salt. There might be a way to find the center of an even kernel. Okay, so then we're given this H. Okay. And you're going to get really happy when you see these zeros because then that just reduces the arithmetic. So it's nice to see some zeros. So let's flip this horizontally. Whoops, if I can spell. I am an engineer after all. So now this is going to be the same because it's symmetric around, this is like imaginary like lines. When we flip it horizontally, it stays the same. Same with this. And same with this. Just making sure I'm not messing this up. And then we're going to flip this vertically. Okay. So just making sure I did that right. Yeah, looks good. Okay. So now these are going to be our two matrices of interest. So now let's just make a new page. Okay, so this process does get a little bit, I want to say tedious just because it's a lot of arithmetic, but bear with me here, guys. So basically, let me show you one more time. So we're going to take this center and we're going to align it with each one of these. And then we're going to compute the dot product. Let's actually get this a little away so it's easier to see. So we're going to compute the dot product. So here we're going to take 0 times 11, 0 times 10, -2 times 4, and -1 times 14. And then you can kind of pretend that there's like a bunch of zeros here. So everything that's outside of this will just be like 0. But you don't have to, just keep that in your brain. It's not like actually part of the signal. So just pretend there's like a bunch of zeros here. You don't have to write that. I'm just showing you guys. Right? So then everything on the outside just becomes, whatever times 0. So it doesn't contribute anything. But once you leave, you get closer to the center, that doesn't really matter anyways. So now let's start. So let's start, just so we're not confused, I'm going to erase these zeros. But keep in mind, it's on the edge. We're going to assume it's being multiplied by 0. So let's start with points. Let's see here. Yeah, let's start with just 0.11. So let's just start from the top here. So we're going to start with this guy right here. So we're going to call our output y. I believe that was the variable they used. So output y, we're going to say y of 1, 1. So that's going to be this point overlaid with this point. Once again, just trying to hammer that home. So we're going to have 0 times 11 plus 0 times 10 plus -2 times 4 plus -1 times 14. So I'm going to take a quick pause to make sure everyone understood what I just did. Any questions so far, guys? Okay, I'm going to assume there's no questions, but please interrupt if you're feeling a little confused. So then these cancel, or they'll cancel, they're just 0. And we have -8 minus 14, which gives us -22. So now let's have our overall like y output just be here. And let's put -22 here. So that's just 1 point. And then we do that for each single time point, guys. I'm just gonna get some water really quick. Okay, let's keep pushing on, guys. So let's do y of 1, 2. So now we're going to align this with this guy over here. So we're going to have 0 times 11 plus 0 times 10 plus 0 times 9. So that's this whole column times these 3 guys plus -1 times 4 plus -2 times 14 plus -1 times 5, which is going to give us -37. So that's going to be this guy right here. Okay. So now we're going to slide it over to this guy. So y of 1, 3. I'm going to go a little faster here, guys, because at this point, it's just a lot of arithmetic. But I really want to show you guys how this process works. That way everyone feels good about it. So 0 times 10 plus 0 times 9, that's our center, plus 0 times 8, plus negative 1 times 14, 2 times 5, plus negative 1 times 15. Okay. So that's going to be negative 14 minus 10 minus 15. Doing this in my head, I think that's like 39. Okay. So I'm not going to go through all these points, guys, because at this point, it's a lot of arithmetic, and I feel like the process doesn't really change. But right now, I've showed you what it's like to multiply things on the border. Let's just show you some examples of multiplying things that are on the no border, so in the middle. So now let's see. Let's choose this guy right here. So now let's do y of 2, 2. And then we'll move on to the next question, guys, unless there's any concerns. But basically, you would repeat this process for every single point and then just keep adding to your output matrix here. So your output should have, be the same size as this, which I'll also get to in a second after I complete this. So y of 2, 2. So we're going to align this guy with this guy. So let's just start from the top left. So we're going to have 1 times 11 plus 2 times 10, 1 times 9. And just to show you guys, I'll just move the row down. So then this is going to be 0 times a bunch of stuff. So this is going to be pretty much ignored, but 0 times 4, 0 times 14, plus 0 times 5. Now move the row down. Now we're doing this row times this row. So we're going to have negative 1 times 1 plus negative 2 times 0 plus negative 1 times 1. And I think that's 28. So then this guy would be 28. Okay. So then you would keep doing this until you have, numbers. I'm going to put like an asterisk for like numbers that you would do. Actually, let's do like a square. I don't know. So these would all be points you'd have to do. I'm not going to go through all of them. And what I want to touch on earlier, guys, is that if you're doing this in practice, I'm pretty sure how MATLAB will do it is it'll actually start like all the way over here. So it'll take this negative 1 times 11. And you'll see in MATLAB, if you go to the conv2 code, it says somewhere like the length of your output will be, let me find it real quick. It's kind of important. Yeah, so the length will have, it has m plus p rows and n plus q minus 1 columns. So what that means is that it'll actually start from the very tips and your output will be way bigger, and you'll have to manually like trim your output to be the size you want, because this information like might not be relevant to you, if that makes sense. So it'll start by sliding these absolute outer corners. And so you'll have like the length of, for example, the length of the columns. If you're starting here, it would be the length of these columns, which is 4, plus the length of these columns, 3, and then minus 1. So your output will have columns 4 plus 3 minus 1, which is 6. Just so you guys are, aware of that. Okay. And so let's move to the next question. Actually, I think this might be doubled, right? Because it'll also go up here. So this might also be plus 2, might be 8. I might be spouting nonsense, but just keep in mind that your output will have a different size than your signal X. So you'll have to trim it down manually. That's the main takeaway there. Okay, so part B is now saying a little bit of a different question. We're going to calculate the file size in kilobytes of an 8-bit grayscale image, which is 128 pixels wide in the y dimension and 256 in the x dimension. Okay, so there's a bunch of questions here. Let's just start with one at a time. So let's start by just answering this first one. So calculating the file size. So really briefly, here's a quick example where you have an image here and its length in pixels. And if you know what its, these actual dimensions are, you can make some ratio of pixel to length to find the actual dimensions. And then here's some kind of conversions, guys. So 8 bits is 1 byte. And when you have RGB images, each pixel here, if this is like a pixel, will have like some RGB values. So this is RGB. It might be from like 0 to 256 or 0 to 255 or 1 to 256, but it could be like 100. It's a lot of green. So this would probably be bigger. I'm not sure. I'm just like guessing here, right? So RGB. So if you're doing RGB, you'll have a 3 times greater size than just grayscale. Okay, so let's hop into the question. So trying to find the file size in kilobytes of an 8-bit grayscale image, 128 pixels wide. Let's draw a little picture here. Hundred 128 pixels wide in the Y and 256 in the X. And it's 8 bits and it's grayscale. So we don't have to worry about what I just said with the RGB. 8 bits, grayscale. Okay. So to find file size, this is a little bit of, I guess, unit analysis. So our bit resolution is going to be 8 bits per pixel, because that was given in the question. And to find the total number of pixels, we just find the pixels, like the area of this image, right? So we'd have 128 pixels times 256 pixels. Okay. It's a little smaller. And we have 8 bits per pixel. And the end goal is to get it in bytes, right? Because we're dealing with size. So then here we can say that there is, for every 8 bits, there's 1 byte. And this is a little bit of an important note, guys, but for 1 kilobyte, it's not going to be 1,000 bytes. It's going to be 1,024 because it's base 10, right? So 2 to the 10. 2 to the 10 bytes. So then after all this, multiply everything out, we get 32 kilobytes. Any questions here, guys, before I move on? So we just drew a quick picture. I think it's always helpful. Write down all the information you have. It's a good strategy always. You don't have to worry about this RGB stuff because it's given that it's grayscale. The bit resolution is 8 bits per pixel because that's given in the question. And you just convert these pixels to kilobytes with some unit analysis. Everyone feeling good? Can I get a sea of thumbs up from everyone? You guys still alive? Wow. Thanks, guys. Okay. 2 thumbs up. I'll take that. 2 is all I need. Okay, so that's one question done. Boom. All right. What would be the file size if it's an RGB image? Well, I'll work through all the math again, but you could basically just do this and times it by 3. So we already know the answer is going to be 96 because the RGB will store 3 times as much more information because it's for each point here. So this is RGB, but if it was grayscale, grayscale, it would just be one number from 0 to 255 or 1 to 256. So if this was black and white image, it looks pretty dark. I think that's going to be the higher numbers. I'm not 100% sure. So it might be around 200. If it was black and white, but it's not black and white, it's RGB. Anyways, let's go through all the work one more time, just so you guys can see the thought process. Maybe he won't ask it in this way, and from the beginning, you have to figure out the size of an RGB image. So you basically start off the same way again by finding the area of the image. And we know the bit resolution.
Maybe get rid of the 32 kilobytes equals 96 kilobytes at the top. That's not true.
Yeah, thank you. So just for you guys' understanding here, we know just intuitively it'll be times 3. But let's go through the work one more time, in case he asks it in a different way. Okay. So then we know it's going to be 8 bits per pixel. And the thought process is pretty much along the same lines, guys. So 1 byte is going to be 8 bits. And these unit conversions, I'm not sure they'll be given, so you're going to want to have a good intuition about them, guys. So now, for every pixel, we're also going to have 3 bytes. So 3 bytes per pixel. And this is what I was talking about times 3. So up here, each pixel contains 1 number for grayscale. It's going to be the intensity in black and white. But if you have RGB, each pixel will have 3 components of information. So it'll store 3 times as much info, because it'll have info about the red intensity, the green, and the blue intensity. Whereas grayscale is just black or white intensity. Okay? So then once again, let's get into kilobytes.
Probably a little more accurate to do 24 bits per pixel, because if you do the dimension analysis, you get pixels squared at the bottom.
Could you say that one more time? So 1 byte would be 24? No, you're saying 24 bits per pixel, right?
Yeah, because you have 8 bits per pixel and 3 bytes per pixel, and it doesn't quite work out.
Yeah.
So 24 bits per pixel.
Sure. Yeah. Let's try that instead. And then just keep in mind, guys, that this is 8 times 3. So RGB. And this is value, or like intensity, I guess. I'm not 100% sure on the reasoning for why each number corresponds to 8 bits per pixel, but I'm sure it's this is like a common thing, I'm sure.
Wait, is the 8 bits per integer, is the bit depth not in the bit resolution not in the question?
No, it is. It's given here. 8 bits per pixel.
Oh, okay, yeah. So, wait, so
Yeah.
what are you confused about then?
So we are converting, it's given in bits and we are asking for the size in bytes. So we're kind of doing a conversion here,
Yeah. Yep.
Oh, yeah.
1 byte is like 8 bits. So that's why we have like 8 bits per pixel and then 1 byte for 8 bits, because that's the conversion.
Oh, gotcha. Okay, you're confused about why 8 bits is 1 byte.
Yeah.
Is that okay? Got it.
That's a given thing, yeah.
Yeah.
And I think it's better to write 8 bits per pixel and then 3 bytes per pixel, because it's, I think, more intuitive if you're saying it that way. Yes.
Okay. So then here we can just
Yeah, do it 3 bytes per pixel.
Okay.
Because RGB defined the 3 bytes.
Okay, sweet. So back to a little bit of what I had before, guys. So we're looking pretty good here. And so now the last conversion is that we want to just go from, to 1 kilobyte. So now we're in bytes and we want to go to kilobytes. And once again, keep in mind, this is not, very oftentimes you want to associate kilo with 1,000. It is 1,000, but it's 2 to the 10. So this is where that 10 comes from. Well, it's not, I guess it's not 1,000. It's 1024, right? But it's base 10.
Well, so my issue with this dimensional analysis is that you get bytes twice in the numerator, and it doesn't quite cancel out. So that's why I think it's better to do 24 bits per pixel.
Okay, for now, guys, we'll update this and we'll get back to you. But for now, let's just write
Sure.
like
I mean,
three colors.
It's like super minor. That is true.
Yeah, let's just write like 3 colors. So you're gonna times it by 3 for now. So ignore this. This is like some fallacy. We'll get back to you on this on the proper way for the units. Having a little bit of a debate right now. So overall, you'll get the same answer of 96, which is just grayscale times 3 kilobytes. Okay. So any questions so far, guys? Besides about this little blip, we have to kind of think about for a second. Any other questions, guys? Are feeling pretty good? So we answered this, what is the file size of its RGB, and we did grayscale. And now, like I was mentioning before, we can assign each pixel its own length in this, like, if you want to think about it like the real world. So if we know the length of this, I don't know if you guys have used like image J, but this is kind of like how it works, where if you know like this is a certain length, you can assign, each pixel its own length. So here the question is asking us if the image represents a physical length and width of 51.2 centimeters and 25.6 centimeters respectively, what is the area of each pixel? So we're given the overall dimension of the whole image, or the overall size of the whole image. So here, I think it's always good to draw a little picture. But overall, the math is pretty straightforward, guys. But just to hammer it home. So here was our initial image. It's still the same image. And we're given that the width is 25.6 and the length is 51.2. So this is 51.2 centimeters and 25.6 centimeters. And so what this looks like, guys, is just the area of the image. Sorry, backing up a little bit. Let's find the area of each pixel, which is what the question is asking for. Area of each pixel, we can just take the area of the image divided by number of pixels, right? So nothing too crazy. This is not some convolution or anything, but you're going to want to make sure you understand this because this is kind of like the foundation of image analysis. So here we can just write 51.2 centimeters times 25.6. So we assume the image is a rectangle. We're just doing length times width to find area, nothing too crazy. And then to find the number of pixels, 256 times 128. These are pixels. So what we get is that each pixel will represent an area of 0.04 centimeters squared. Any questions, guys? Let's get a sea of thumbs up. There's only a few of you, so I might call on you guys. Isabella and Jade, you guys feeling okay? Any questions about any of these, even from part A? Or are you guys feeling pretty good? Okay, I'm gonna assume you guys are feeling pretty good, but if you change your mind and a question comes up, just drop it in the chat. Wow, thanks, Isabella. I ate this question up. Yeah, I did. Gobbled it up. Thanks, Isabella. But if you have any questions, yeah, change your mind or anything. My final note is that I would highly, highly recommend like watching that YouTube video in the chat. I would say, take your understanding to the next level, and you'll feel good on the next test. Okay. Thanks, guys. And keep working hard. You guys are doing great. You're more than halfway through the semester, and test 3 is done. So just keep working hard, and you guys will be, doing great. Good job, everyone. Okay, on to the next person. So who's going next, guys? Question 2.
Oh, I think we're just jumping to the code. Apologies.
Oh, okay. Just making sure.
All right. Just a second here. All right. Is everybody able to see my screen all right?
Yeah, we can see it. Looks
Okay.
beautiful, Ryan.
Perfect. So I have some sample code here for some image processing stuff. And I'm just going to run us through it, kind of explain what's going on and some possible applications of this kind of stuff. And you can refer back to this video, or I'll have to talk to the lead TA, but we might upload this sample code from the recitation. But at the very least, you'll be able to refer back to this video. So off the bat, we're just clearing everything, clearing our workspace, closing all the images, everything. So this is not anything particularly exciting. So now we want to go ahead and import an image. So MATLAB has a lot of functions that make this easy. The primary one, if you just have an image file in your workspace or in your folder, is to use imread and then provide it with the name. And as long as it's in the same folder as the MATLAB code that you're running, it will just pull that image and import it into MATLAB. And then this is just plotting the image. So we can go ahead and run this and we can see, we got a nice, beautiful landscape somewhere, probably in Switzerland, who knows? But we got a nice, beautiful landscape. All right. So we can use imread and the file name to, we can't see the pop-up. Okay, hold on. I have to share my whole screen in that case. One sec. All right. Okay. Let's try this again. Are y'all able to see the pop-up now?
Yes.
Okay, perfect. All right, we got a beautiful landscape. We're in the Swiss Alps. How does everybody feel about being in Switzerland? I hope you all feel good about it. All right. So we can use imread with the file name to import our file, save it as a variable, and then plot it. So now we want to take our image and we want to convert it to grayscale. So once again, MATLAB has a super easy function to do this. RGB to gray. So this particular function, all it's doing is converts an RGB image to a grayscale image. Its whole thing. So this is a good function to know, but we can take our image that we imported up here, pass it through the RGB to gray function, and it gives us a gray image. So we can go ahead and see that. Beautiful Swiss Alps, but gray this time. All right. So this is pretty simple. So far, we've really only used two functions and then subplot to plot it. Now, let's see if we want to rotate this image. Once again, third time's the charm. We got a really easy function to do that. So we can use imRotate, and we give it the image we want to rotate and the angle that we want to rotate it by. So in this case, we're going to take our gray image and we're going to rotate it 180 degrees, which is just going to flip it straight on its head. So let's go ahead and see that. So now we're in the upside down Swiss Alps. So we can just use this function to rotate our image, and we can change this value to whatever we want. It works better in increments of 90. but it will let you do other angles. It looks kind of amusing. So you can use this to correct if you have an image that's slightly off axis and you really need it to be on axis, for example. You can use this to correct it, rotate it by, let's say, 5 degrees, and that puts it on axis. And we can even make it rotate it by 90, make it vertical. All right. So we've gone over these 3 functions. IMRead, just to get the image in, RGB to gray, to convert our RGB image to grayscale, and then IMRotate to rotate our image by some amount. So now I want to ask y'all a question. So what do y'all think this code is doing? And do you see any differences in these images? If anybody wants to take a stab at it, I'd appreciate it. Anybody?
Is it sampling the different luminosities for each of the RGBs?
Yep, that is pretty much exactly what it's doing. So we can see here, we're taking our sample image, which was our original RGB image, and we're taking all of the rows and all of the columns, and then 1, 2, or 3 from our third, what do you call it? Dimension, I guess. And what each of these represent is a different colorway for your RGB image. So I don't, Amelia, do you know off the top of your head which one corresponds to which color? I don't remember that off the top of my head.
I think 1 is R, 2 is green, and 3 is blue.
That would make sense, but I'm not positive on that. But regardless, it's taking each of the colorways and graphing it or displaying it. So we can see that this is 1, this is 2, and this is 3. So let's say this is red, green, and blue, although I'm not positive on that, but let's just run with that for now. So you can see the images are very similar and you can still see the image, but it does change the image slightly. You can see this area in this image is much darker than on these 2. And the area under the house is much darker, etc. So this section of code is just taking each colorway. Now we get into the really exciting part. So let's perform a fast Fourier transform on this image. So what we're doing here is we're taking our grayscale image and we're performing an FFT2 on it. And this particular function is a 2-dimensional Fourier transform. And it's equivalent to taking the Fourier transform of the Fourier transform of something. And in this particular case, you use it because we have a 2-dimensional image, right? So we want to use a 2-dimensional Fourier transform. And that gives us our transformed image. And then down here, we're going to go ahead and plot it. So first, let's comment out this stuff. And let's just see if we take our image and we transform it, and then we're going to take the absolute value in here just to get rid of any negative frequencies, because in this case, we only care about the real frequencies. So let's go ahead and see. So this is our Fourier transform without center. And it kind of just looks like a mess, right? So there's not a whole lot of information here, but this is our Fourier transform. Now, let's go ahead and let's apply a fast Fourier transform shift. So what this function is going to do, I think it's easiest displayed with some of the graphs in this, is it's going to take our signal, or our Fourier transform, and it's just going to center it around 0, right? So this goes from 15 to 85 roughly. And then it just takes that and it centers it around 0 with the midpoint on 0. So we can take that and apply that to our transform. And we're going to shift our transform. And now this looks a lot more promising. So here we have our Fourier transform that's been centered. So we have our highest intensities. And then as we move out, we're getting lower and lower, etc. And this we can use to do a lot more things, which we'll get into in a moment. But this is our centered Fourier transform. Now, let's see what happens if we take our Fourier transform for our rotated image. So we're going to take our rotated image. We're going to perform, this should be that. We're going to perform a two-dimensional Fourier transform on it. Get the transform. We're going to shift it and take the absolute value to get rid of any negative frequencies. So let's see, what does that look like? What would you look at that? It looks almost identical to our centered Fourier transform, but rotated 90 degrees. And if you go back, we can see that we took our image and rotated it 90 degrees. So there's actually a relationship between our image rotation and our Fourier spectrum rotation. So they both got rotated 90 degrees when we rotated the image. But now we have our Fourier transform without centering, our centered Fourier transform, and our rotated Fourier transform. And we did that with one simple MATLAB function, just FFT2, take the second, the 2D Fourier transform. And then we took the absolute value and shifted those and displayed them. Any questions so far on this particular stuff? Thank you, Jade. I think it's cool too. I do image processing for my research, so I don't do this exactly, but I do some similar stuff and I find it very exciting. So I appreciate that you also appreciate it. All right. So now that we have our Fourier transform, we're going to take our transform and we're going to shift it, just the same thing we did up here. We just didn't save this as a variable, so we're going to do it again. And we're going to save it. And then we're going to find the size of our shifted Fourier transform. So that gives us our X max and our Y max. And we can use that to find our dimensions of our image. And then we're just going to declare an array that is zeros at the same size as our image. And we're going to create a second one based off of that. That's just the exact same. So these two arrays are just going to be zeros from 0 to our x dimension and to our y dimension. And now we can find the center by taking our maximum x and our maximum y, dividing it by 2. That'll give us the center of the image. And then pixels always have to be integers. So we're going to go ahead and round that to a whole number. And that will give us the center of our image. So now we can go ahead. We have the center of our image and the dimensions of our image. And we can now apply some filters to it. So we can do a low pass, high pass, and band pass filter. And these are all kind of used for different things. So low pass filters are commonly used to smooth out an image and get rid of all the really high frequencies. which kind of gives a smoothing / slight blur effect to the image. High pass filters are getting rid of the low frequencies, and they're commonly used to kind of sharpen an image. And then band pass filters get rid of the really low and the really high, and they're commonly used to, I've used them in the application of edge detection. So it'll make the edges in your image more defined, but they can be applied to a number of different things. So they all kind of have different uses, and we can go ahead and select what we want our frequencies to be. So in this particular case, we're going to take our frequencies to be 35 and 50. So what we're going to do is for our low pass filter, LPF, we're going to take the center of our image and we're going to subtract and add. Sorry, this is, trying to think how to explain this. So our low pass filter currently, this is just an array that's defined as a bunch of zeros. So it's just a whole big, let me actually, I'm going to comment all this out so I can run it and just show y'all. So, oh, I need to comment this out as well, huh? All right, let's try that again. All right, so all of our filters at this point are just a whole array of zeros that are the same size as our transformed image. So they're 1414 by 2200, right? So now we can take that, and in this section of code, this section is the indices that we're going to use for our low pass filter array. So we have our center value based on our image. And what we can do is we subtract and add our frequency from that center in both the X and Y direction. And that gives us our indices of the center minus our frequency to the center plus our frequency. So let's say our center is at 100. This will take all of the points in our array from 65, because it's going to be 100 minus 35, to 135 in the X direction. And then everything from 65 to 135 in the Y direction. And it's going to set them equal to 1. And then for this one, it's going to do the same thing, but we're going to use 50 instead of 35. So it's pretty much the exact same, except we're going to apply a different frequency to it. And the reason we do that is because once we define these arrays, we can manipulate them and multiply the images by them to apply a filter to the image. So we take our low pass filter and we multiply it by our image. And let's see. Let's take a look at the low pass filter. So look at that. We only have, from the center of our image, we only have 35 pixels in each direction. Everything else has been turned into a 0 because we originally had our low pass filter array was all zeros. We changed this section to be 1, and then we multiplied it by the image. So this center bit is going to stay the same as it was in the Fourier transform, and everything else is going to get multiplied by 0 and become 0. Does that make sense on how we kind of build our filter and apply it? Any questions there? I'm gonna take that as a no. I hope you all are following. So now, if we take our low pass filter and we take 1 minus our low pass filter, it's going to give us the exact opposite, which is going to give us a high pass filter. So we can go and plot this. So we take that and our high pass filter. So let's take a look at our low pass filter again. So you can see it's all zeros, except for it should be right in the middle somewhere. Where are the ones? Oh, here we are. So it's all zeros except for this center region that we turned into ones, right? So the low pass or the high pass filter, we want it to be exactly the opposite. So as you can see, this is all ones, except for the very center should be zeros. And that's because we took 1 minus our low pass filter. So we basically set all of the points to 1, and then we subtract off our low pass filter. And if you remember in our low pass filter, all of these were 0 and all of these were 1. So 1 minus 0 just stays as 1, and 1 minus 1 goes to 0. So now if we plot this, we can see for our high pass, we have the exact opposite of our low pass, where 35 pixels in each direction around our center are going to be 0, and everything else is going to be our Fourier transform. And for bandpass, we just take the difference between our two frequencies, the arrays of our two frequencies, and multiply it by the image, and then do the same thing. And that's going to give us a bandpass where we only have between 35 and 50 pixels in each direction based on our frequencies, or based on our cutoff frequencies that we define. So now, can we get our image back after we've transformed it? Well, yes, we can. So we can use the inverse fast Fourier transform, and we want to specify that it's a 2D inverse fast Fourier transform. We can apply that to our image, take the absolute value of it, and then display it. And that should give us our original image back. And in this case, we have it scaled by a color. So as you can see with the low pass, it filtered out all the high frequencies and it kind of smoothed out this whole image. With the high pass, it sharpened the image by filtering out all the low frequencies. And then I don't know what happened to the band pass. This is quite interesting. I don't think the band pass gave us a whole lot of useful information or a useful transform on our image. But we were able to take the Fourier transform of our image, apply different filters to it, and then get different effects when we inverse Fourier transform that back. So we want to take a look at everything. We took our original image, our beautiful view, made it grayscale and rotated it. We examined what the different color channels kind of look like. And we found our Fourier transform and centered it. And we saw that there's a relationship between rotation of our image and rotation of our Fourier spectrum. Then we applied different filters to our Fourier transform spectrum, a high pass, low pass, and band pass, and then inverse Fourier transforms those spectrums back into our images with different effects applied. All right, any questions on that? Yeah, I think you're right, Jade. I think if we made the band pass a bit wider, it would have been beneficial. I mean, we could try that. Let's see. Let's go 25 to 75 and see what that does. So let's go ahead and just run this again. And yeah, there we go. it's still kind of murky, but you can see more of the actual image there. All right. That is all I've got, unless y'all have any questions. I hope y'all kind of enjoyed this demo and took something away from it. These are just very simple applications of these kind of concepts that we're learning about. But it's nice to see it done, I think. So it's similar. So they get similar results in a different way. That's I'm not sure exactly how they work, but so that's as far as I'll say. But yes, they do get similar effects. I think for the Gaussian blur, your blur is going to be stronger in the center of the image just due to the nature of a Gaussian blur, versus this should be smoothed out evenly across the image. But take that with a grain of salt because I'm not positive on that.
I think that's like a different filter function.
Yeah,
Like
they
if
are
it's a-
different,
Yeah,
but I think they give you similar outputs.
yeah, but like I think it's only for like the frequencies that you're like. I think it's only for certain frequencies
Mhm.
that you can kind of absorb that.
All right.